Okay, and I'm recording as well.
Alrighty. Well, welcome and bienvenue to another night, NeurotechX Hack Night. And I'm Morgan, your co-organizer this evening, and we have a great lineup tonight. So we are have been actually going since this morning for BCI 101, which I don't know if anybody's caught, but this was the wrap up of 3 weeks of BCI lectures and presentations that included today Ramses from Neurables, who was one of the first demos that I ever caught at a NeurotechX event, demo days back in 2015, if I remember right. And so it was Neurables. Who were some of the? Did anybody else catch that today?
Mind Effect was there.
Yeah, Mind Effect. Yeah. So and I don't. Jaden, did you get a Mind Effect device? Oh, okay. What? That seems very small.
It's just it's a Raspberry Pi that they have all their algorithms loaded onto, and you just stream the data from the BCI headset to the Raspberry Pi, and the Raspberry Pi does all the prediction and classification and streams it to whatever. And it's a really intricate setup how it lines up the timing of whatever computer or iPad or whatever you're using, and it times it perfectly with this. It's pretty cool.
That's cool. I did not know that. I got a bunch of questions. Now that Mind Effect in particular, and he talked about this today, is a spinoff from Donder's BCI. So I assumed that there would be a lot of GitHub repositories that we could look at and things, but I didn't actually. That's very cool that they were shipping on Raspberry Pi, and certainly there's no reason that most people's processing could be done by a Raspberry Pi. And what's the hardware? Is it just a single channel?
For the EEG?
Yeah.
It's they use the OpenBCI headset. Okay. Their developer kit they shipped with a ganglion board and then a custom headband that they made with certain electrodes. But you can configure it to work with the site and then also consequently with their Ultra Cortex Mark IV.
Okay. Okay.
Do they have a diode or another channel for the screen?
It can go on whatever you want to program it on. So I can put it on a Unity interface on, I think they have some iPhone applications that work with it. And then it just connects to the signal from the Raspberry Pi and times it up nicely.
Are you thinking triggers, Omar, or what?
Yeah, I was thinking more triggers, exactly.
Like if you're doing an ERP experiment, can you get any timing triggers?
How do you mean? What do you mean by the timing trigger?
Well, so I think you would be able to. So potentially, hopefully something simple. I mean, usually with bigger equipment, you might have something like a DB9 cable or some cable that you can plug into the device or plug into the amps. But with consumer devices, it's super hard, right? Like getting a timing trigger for a Motive or Muse is kind of impossible, and that was kind of one of the reasons for impetuses behind LSL was how can we synchronize devices and kind of pass timing information with when we don't have these nice hardware triggers. Yeah, so that came up a lot. But now if they're Bluetooth to the Raspberry Pi, then potentially you could have there's plenty of inputs to the Raspberry Pi. I mean, you could have nice you could use the Simon, what's on the Raspberry Pi? It's like a SPI, isn't it? Sorry, I don't know if you have your mic.
Yeah, no, I've got a double mute thing I have to take off before I can respond.
The Raspberry Pi's got doesn't it have like a 40 pin input on the board?
Yeah, I mean the GPIO, the general purpose input output ones.
GPIO, yeah. I mean, you could have
those.
some really simple. Now it's still Bluetooth, right? I mean, it's
so for the Citon they use the BLE dongle, and then for the timing triggers it's all done over the Wi-Fi network, Wi-Fi hotspot.
Well, you can put there, like we're already trying to do internally, just to revive an old community post from Chip Audette, was we're doing external triggers using a photodiode, and the Citon has 4 pins. It depends on the configuration you're using. I think you should be able to do an external trigger with the ganglion plus the Wi-Fi shield.
Yeah,
And the ganglion may. I can't recall if the ganglion itself can do external triggering. It might have the pins, but maybe it's not. It didn't pan out. I don't know. Yeah, that's something worth looking into.
Well, still that's cool. And is that already compatible with BrainFlow?
What?
Sorry. Well, it is because it's OpenBCI.
They actually do not use BrainFlow yet. They're working on updating the software to use the BrainFlow API, but they wrote everything before BrainFlow was released a couple months ago, and then I assume they just didn't want to delay their release.
Did they really use the Node.js drivers?
Yes.
Oh my gosh.
I know. It's unfortunate.
Okay, just for everybody that may not be, the previous backend for our OpenBCI stuff was in Node.js, and it was a nightmare to maintain. I got scared every time I tried to build the Node.js repositories again. And from a developer standpoint, I don't want to work with Node.js that much because of what can happen with dependencies, and then now your whole app is in jeopardy.
So the current GUI is still on Node.js though, isn't it? Or did they release the BrainFlow GUI?
We're working on that. It's coming out next month.
Okay.
We've got a schedule. We're working hard.
Very happy to hear that.
Well, that's great. And interesting. So does Mind Effect, do they open source all their code?
They do not, but I spoke with Danielle a while back. She's in the Slack group, and she talked about that they're thinking about open sourcing it down the line at some point, just because it's already, on the SD card. And I could take it and share it with whoever I want right now. I'm just not going to because,
Sure.
rude. But yeah, it's they're thinking about open sourcing it.
Can I ask a pretty big question? We talked about gamification in the BCI 101 NeuroBar. Is it fun? Have you had fun with it? Or is there a barrier to fun currently?
I'm still trying to get it to work consistently. We got a working demo once, but I think it was actually just a very, very lucky stroke of RNG because we were only using a 4-button selection, and we had 4 correct classifications in a row for the demo that we were doing. But I think it was just a fluke because since then I haven't been able to do anything along.
I gotta say you're ahead of the game on me as far as I was going to ask you if you're getting good signal, that you're connected properly. That's the most important thing for me to help new users do. But I have all this hair and you don't, so I don't think you're worried about connecting electrodes to your head and impedance. Probably really good.
No, yeah, I've been looking actually at the William shared that link with me to the Florida Research Instruments website, and I've been looking into getting some of their flat electrodes and just designing my own thing that I can connect to the site and make use of all of the scalp real estate. Did anyone else's audio cut out? Or is that just me?
Yeah,
Okay.
mine did.
Sorry. Okay. Yeah. Sorry. We had
About a good 30 seconds there was lost.
kids coming up the stairs. So let me start that again. So John Chivuk from Blueberry, who was joined us last week talking about his single channel NIRS glasses that just got funded on Kickstarter. I talked to him on Tuesday, and he's going to have an engineer look at some of the PyGAT issues that we had. So this is this kind of separate from what you've done, Jaden, in terms of bringing BrainFlow into EEG notebooks, which is awesome in terms of allowing us to support multiple, not only OpenBCI but other the GTech Unicorn and BitBrain, which was also part of BCI 101 on yesterday, I believe, right? And so the Muse though has we still had this issue that Simon and Andre Shmakov have looked at, where anyway we had to comment out some code and to get things working, as well as the fact that we're still tied to this particular Blue Giga Bluetooth adapter for the Muse compatibility. So and we know that that's not we know that's really a software issue, because projects like Kyle Matheson's EEG EDU are working fine with JavaScript. I forget what JavaScript project they're using for.
React.
Yeah, and that's right. And so that's awesome, because they've got a lot more experience there. I mean, he's not with Interaxon, but I believe it's some some people there. There's a lot of overlap between the people there, and he's in Steve Mann's building, as we also got to see last week. So that was my news bit, and I don't know if anybody's has followed. So Brainstem 2020 was also this week. So a really great conference that is happening in Finland, where they're building. So Finland has this really long history with MEG, and because they've been into MEG and that kind of technology, they're also really strong in source imaging. But they are. It's a particularly interesting place because of what they're trying to build in terms of a multi-coil TMS system. So they got, I think it was, €1 million for this whole head. So if you imagine like a helmet that's all little coils, and doing field shaping. So Brainstem 2020, all those are on YouTube, as well as they did their poster sessions on combined web YouTube poster session. That was also
Morgan,
good. Yeah.
Would you like to share the link?
Sure. Brainstem 2020, and I will. Let me. It should be that. Yeah. Brainstem meeting. Oh, I'm just seeing your comments there, Simon.
Sorry, I stepped away for a second, but one little comment I have just for Jaden. Did I get it right?
Yep.
Yeah. Find me on LinkedIn, man. Cool stuff. But the ganglion, whenever there's packet loss on the ganglion, there's another support thread on the forum that's actively happening right now. And he's like, I got little spikes. And I told him, your battery might get low because the Cyton battery that's low, it will drop packets really bad and it will throw a hissy fit. But the ganglion, when it drops packets, even in the GUI, it doesn't make any blips or anything, even with our archaic filters that we're about to replace. We're going to end up using the filters from BrainFlow eventually because they're C++ based, and then they end up getting bounced straight to a Java library, and it's real fast. But that's one of the benefits that MindEffect has going for them. Using that ganglion to BLE to the Raspberry Pi, it looks pretty good. I've walked outside all the way to the garage, and then I come back and look at the recording, and I can't seem to find a difference. And that BLE will reach it'll reach a lot farther than you would think, even through walls.
That's interesting because I have a lot of trouble with the Cyton dongle.
Testing, sorry.
No, it's okay. I have a lot of trouble with the Cyton dongle when I'm around any type of remote, anything else that might be wireless at all. I have to shut it all off to get no packet drops. Yeah,
and the number one thing that probably users get into, I've seen this a lot, is they don't plug the unit up to their head. So it's basically picking up nothing but radio interference. And they're like, why is it so noisy? And then the next common thing is that the ground references aren't connected to the ears properly. And so the next change I'd like to make is having some pictures for everybody that clearly labels saying this is where this is plugged in, and it goes off and plugs into the ears this way. But,
if I could make a suggestion, even I think a video of someone putting the headset on and then properly adjusting the electrodes and showing the whole setup process would help a lot. Because I had a lot of issues at first with putting the headset on and then trying to turn the electrodes but forgetting that they're still plugged into the wire and having to unclip, do that all over and over again. So
hey Joe.
Richard, how's it
I
going,
bet
man?
you didn't expect to see me here.
I had a suspicion.
Yeah,
You've been on this since 2 p.m. today, right?
Oh yeah, going full conference mode, learning as much as I can, getting my mind blown by peers.
No, the BCI 101 stuff is as someone who used to organize concerts and events and things, an awe-inspiring feat of international organization.
Yeah.
So we were just saying it might be helpful to. Jaden was saying just to have a video of somebody putting the headset on and adjusting that, and so I'll add that as an item. So I'll try to get it out.
So Joe, thanks again for joining us tonight. I always appreciate East Coasters joining us, and value your late evening. Okay, yeah, absolutely. Seltzer water, but yeah, cheers.
Yep.
So wanted to touch base with you, and I was actually on a call with Yannick and John Griffiths and a bunch of other people, so that's probably why they're not here yet. But that wanted to just see if there's anything else that we need to talk about in terms of, so Jaden's with us here, who's, already done the work in terms of incorporating BrainFlow into EEG notebooks.
Yep.
So, and giving, and that gives us a number of prepackaged experiments. There's still a couple things that I'd love to add to that. I mean, that'll be, super easy. Not really experiments, but more wrapping it all together. Maybe having a few directions in terms of, getting people to move their eyes or getting them to blink, and, capturing some of that as a part of a larger set of experiments in a particular subject. And then, we would, like, if we make changes to Eeg notebooks in terms of what it outputs, as opposed to just being, adding more metadata that includes, experimental design and things like that, so that you can more quickly go straight to analysis, even if we're, sharing these. And yeah, so those are some of the things that we had previously talked about, both with you, Joe, and on our own, just in terms of how best to refactor. We want to bring Jaden's work really into the main branch of Eeg notebooks. But yeah, so anything new on your side of the country?
Yeah, I don't think I have any, like, my interest is to do some sort of activity this summer that more than 10 people can participate in.
Yeah.
You know what I mean? Like, that's it. This is the maximum requirement from my end. We have some marketing budget that was supposed to go to events that doesn't have, all those events have been canceled. So I'm looking for some way to involve, I'd rather involve a smaller group of people that are actually interested rather than like a huge group. And I'm just trying to figure out, like, I am not the right person to sort of figure out what is the problem worth solving. That's what I'm looking for assistance on. And some sort of crowdsourced contest or challenge where there's an objective, there's a way to judge success versus that objective, and then it's open for a certain period of time, July and August or 2 months or something like that. And I think there's, I had one of my ideas was just to simply, there's a 3D printing challenge that can happen with, like, I know that's like, hey, design an enclosure for some of the OpenBCI hardware that we put out there. People have asked for that for a while. It's a solvable problem that people can approach from multiple different ways. And, like, I think that could be one thing. But as far as the EEG notebook stuff goes, like, I guess I don't understand it well enough maybe to, like, propose the way forward. What it seems to me would be, there's a data collection element, and then there still needs to be some way of judging, like, there needs to be like a task and a categorization for that task. It seems to me like one of the things that would be most common is like, okay, we're going to set up, the ability to collect eye blinks and remove them from data, or, removing an artifact, or it's, I don't know, just, like categorizing some sort of ERP. And I think there's like data collection, and then there would be, create the best way to identify whatever it is that we're sort of focusing on. And then we would rank that, based on entries.
Sure. I mean, so certainly what we were talking about last week with John, who hopefully will join us a little bit later. He might have been like me, where he also needed to take a break from a full day of BCI 101 and maybe grab some food. I was just brought some pizza, some leftover pizza, but. Yes, that what people would get from contributing their data was basically access to the group data, right?
Yep.
And so yes, like what you would get, I mean, what you could then do is, like, I've done some automated eye blink removal, and, like, this is what the ERPs look like when you've run my my particular cleaning algorithm through those, or maybe somebody's trying to pull out some particular feature, as opposed to suppress a particular feature, and that it would be like that. Hopefully you'd get this interest in contributing the data, because you'd get access to a lot more data.
Yeah. Jaden, I mean, what are you interested in and sort of, you know what it's capable of. And I think you might have a better idea of like, how could a group of people contribute to what it is that you've been working on? And, do you see a way that it can be applied that builds something, that's useful for later?
That is an interesting question because what I work on specifically is a little bit difficult to collect general data from because it primarily involves people with intellectual disabilities.
Okay.
And so it's a lot of
It's an isolated population.
Yeah, and so a lot of the work I do before getting to work with the actual subjects is mainly theoretical and just doing a lot of case studies on what can be done, what kind of paradigms will be useful and things like that. What I would say would probably be maybe really useful, just generally speaking, is one of the biggest problems that's always plagued BCI algorithm development is generalizing across subjects. And something that at least the Riemannian geometric classifiers seem to be pretty good at, but it would be beneficial to have more data across different subjects for all kinds of different paradigms and then develop like a good algorithm or good pipeline that generalizes across people. Specifically for the OpenBCI headsets even, that would be very useful and especially useful for people who continue to use them.
Yeah, that makes sense.
But I don't know how much of that is above or like at what point of the general user base.
Yeah, and I think what we just need to, we probably just need to set aside some time separately on our own calendars to like sit down and really talk about this and figure it out. I can do some, I know Andre's been following along on the OpenBCI side of things, with your progress with the EEG notebooks and, sit down with him, get familiar with where it is now and just discuss like, hey, how could this be applied in a way that we're building something that's just going to be useful for later. Like that's the real, all I want to do is come out of this with like, we did some activity where a large enough group of people were able to participate and there was an output at the end of it that's like open source and available to use for other people's projects in the future. Those are like the sum total of my objectives. And then everything else that goes into that, I'm open for ideas on what is a good way that can be directed.
I was looking at this as a lesson plan. Well, the first thing you should do, and what college professors are quite familiar with, is you first need to make your rubric, and I forgot what it's called, that they hand out at the beginning of the semester. The syllabus. You make a syllabus, and then that's it. You've given it from day one what's going to start, how you collect the data. That's what how we start is. And then there's going to be a phase of like the submissions are closed. And then with the rubric, there's going to be rewards. Y'all are already talking about that. Rewarding participants with the access to the data from everybody else. So having rewards in place for everyone, and then maybe a small group, and then as for the individuals. So maybe having different types of rewards throughout that process, but then making the rubric first and saying, how are we going to score this? What is success for the project?
I remember, I think I brought up last time we talked about this, the need also for a solid motor imagery paradigm to be used with the OpenBCI headset. So that can also be of interest, finding the proper paradigm to use for recording, and then finding a way that, more people can use it and get a good algorithm for it.
And certainly that is definitely, a kind of complementary project to EEG notebooks, of course, is MOAB. And what MOAB is giving you is two things, right? So one, it's this framework to really test a bunch of different, test your classifier against a bunch of different data sets. But you can also use those data sets to go. Okay. Yeah. So did you want some pizza? you can use those data sets to give yourself, a boost in the data analysis or the even the real-time analysis that you're doing on that subject. And I put another link in the comments. So I wanted to point out the Hackaday, the Hackaday Prize, which, I don't know if others saw this, but so Hackaday, obviously great maker, open, well, okay. And great hacker site, which is funded by SupplyFrame, and anyways, SupplyFrame set 4 challenges for this, and I think each has a $10,000 prize. The third of which is focused on cerebral palsy. And I thought that it would, be quite likely that, especially, since NeurotechX is very heavy with students in terms of student club activity. I feel like, I know I've seen previous student projects that would have been potentially relevant. And yeah, so I don't know if there's any additional synergy there, but in particular, thinking about motor imagery and maybe remote control of devices and things like that. That would be I don't know what the timeline is on that, but definitely wanted to put that in the.
Yeah, Hackaday is great. I
mean, Hackaday is awesome, right? And I was saying, like, we were if it hadn't been for COVID, 2 weeks ago we would have been in Belgrade for Hackaday Belgrade. SupplyFrame's co-founder is Serbian, and they host great events. I mean, they're really and their SuperCon is in the fall. I don't know if anybody's ever gone, but they really great set of people that and this Monday on the Hack Night Paris, we had Luc Janvaux, who's got the open source ultrasound project on Hackaday. And that we recorded that. He should that video should be up on NeurotechX's YouTube pretty soon. I certainly like the I like the motor imagery too, Jaden. And I in particular because it draws on what I think is an underused project, which is Moab. I mean, in terms of not just being a classifier tester, but actually giving you a lot of data that you could use to actually make your algorithms better.
So I'm a lay person. Are y'all talking about asking a person to move their right hand, then move their left hand, or just think about it?
Just
that's
think about
as simple as it is.
Just thinking about it.
Yeah, I mean, that's something that's something even people with a disability can do if they can, have the wherewithal to do it in the right order. I mean, it doesn't matter if they have the limb or not. Those people can now participate too. That's the things that, like I was saying earlier, designing, it's just called universal design for learning. That's what I'm using. It's designing things for everyone and then making accommodations for a few, and then even more specific tailoring to individuals that need it.
Abby,
No, cool. I'm in favor. It's cool.
Well, I mean, I certainly the experiments that we were talking about are already in. I mean, the ERP experiments and the steady state VEPs were already in Eeg notebooks. So, I think the extra bits would have been like, how are we going to actually share data, and what else are we going to put into the files? Motor imagery wouldn't be that hard unless, a lot of motor imagery, or certainly a lot of the kind of BCI frameworks for motor imagery have, like real-time feedback. I mean, so again, like BCI 101 had some really nice presenters of BCI paradigms, that motor imagery paradigms, and that those would be new developments, but I wonder how much people have already done those. I mean, in the sense that like what we'd be kind of looking for. I wonder how much. So one of the kind of co-organizers with Mikhail Lebedev was Alexei. I'm not sure I can pronounce his last name right, but Odestachi. But he's also there in Moscow, and his NFB, I think, is the name of his. Oh, hi, John. NFB, which is a neurofeedback BCI framework. I wonder how much it would potentially have useful features, but yeah, integrating that with Eeg notebooks would be real work, as opposed to the ERP stuff that we already have coded up.
What was it called?
I want to say it's NFB. Let me find the link when I've got two hands. But it's Alexei's project.
Is it in Python?
It is. Yeah.
I can integrate it.
Okay. Well, I mean, I like that too. I'm not gonna say no. So, hey, John, Joe's joining us from. Well, you're both on the East Coast, but just more saying we're still super. Everybody's still interested in moving this forward. I think last week we were pretty happy with just having a number of the ERP paradigms, and it being more like getting a lot of people to contribute even better across a lot of different hardware, created some possibilities in terms of what you could then do with the analysis of the group data.
Yeah, that was what we settled down with, wasn't it? It was like everyone contributes, and then the analysis is on all of the data rather than just your own data, which was one other idea that was floated. Any further thoughts on the kind of presenting the competition kind of thing? That was something that we we're thinking through a few thoughts on, right? How to.
I had mentioned just now, like having awards for everybody, then a few people, and then just maybe a one winner, if you want to provide rewards, or just having a reward that everybody who participates receives, and having that clear from the beginning.
Sorry. She ate my food and then left. Yeah, well.
Yeah. So one of the things, sorry, I'm just joining the conversation, so I don't know like what its trajectory is. But we did. So Chris and I did a little bit of work on this, in a sense, in that we tried to. Chris is here, right?
Yep.
Yeah. Hi, Chris. So Chris has an OpenBCI. I don't. And he has a Mac, I don't. So we kind of did a call over the weekend, and we were trying to run Jaden's thing with his OpenBCI on a Mac. And we got so far, but we ran into
I don't know how well that would have gone.
Right. Well, we got the stream going. That was a kind of simple debug, and then but then there was a PsychoPy related problem that would have taken a bit more time than we had. but that, yeah, kind of the bottom line is this is a question. So like I'm actually kind of quite happy to do do a lot of development work on this if we want to push on this, as in like the BCI project, this BCI project within the kind of, you know, idea space that we came up with. But I have a limitation that I don't have an open BCI, and for Mac stuff I don't have a Mac either. So the kind of two solutions to that, if we want to move this quickly, is either I buy an open BCI, which is what I have looked into this, or I've started looking into this with my my like research funds, but that doesn't happen super quickly because it's a like equipment procurement thing, so it has to kind of go through legal, and because it's over a certain amount, so that might not be quick either, or someone donates one to me, or I borrow Chris's or something. We would figure out some kind of like sharing scheme. So all I'm saying is like this is like a time bottleneck on me making contributions
someone
that I'm
very
happy to
special on
do.
the call that you can now tell Joe, who is here, exactly what's going on, and he is the person that handles our what do you call it program, Joe?
The sponsorship program. Yeah, I have no. What are you working on?
Well, so it'd be sorting out, building on Jaden's stuff with the BCI, the Open BCI implementation of the EEG notebooks, principally ERP. So it's like visual ERPs, auditory ERPs. We can do SSV EPs and auditory steady state evoke potentials. Those within EEG notebooks. So, you know, this kind of PsychoPy supported LSL based, you know, EEG analysis experiment running thing that we have. But that was the thing that we want to use for this competition, right? If we're going to do it, that was kind of where we've settled, as Morgan was saying. So the things, there's what we need to do is we need to kind of make sure that it works in enough of the kind of use cases, as in like different machines that people have, potentially different devices that people have, or different models. And we need to maybe do a little bit more work on specifically like one of the one or two or three of the paradigms, and it needs to be kind of repackaged in a way that's easier for the use case that we have in mind here, I think, which is it's not like rocket science, but it's just a little bit of development work to do. And I think there'll be a few bugs along the way. So yeah, I'm happy to kind of contribute some technical stuff to the mission of getting OpenBCI based cognitive neuroscience out to the world, but I need an OpenBCI to do it.
Yeah, that makes sense.
Yeah.
Sorry, somebody.
I'll get one. It's just if it'll take me a while to get one.
No, I understand.
If
John?
I get one by kind of standard means.
John?
Yeah.
Yeah. Meanwhile, Walter offered to borrow his.
Yeah, no problem.
Okay.
Yeah, just send me your info and I'll send it to you.
Good deal.
But there's typically a form, I think there's somewhere that we do it, because I wasn't expecting Joe to give you a decision like right now. I was just making you aware that we have a program for sponsorship, and I think Joe has even done a loan before, which is not like we give it to you for good, but it was like you mail it back to us when you're done or something. Have we done one of those, Joe?
Yeah, we give out hardware for things that make sense, to do it for. This is one of those kinds of things. I guess I'm just trying to still wrap my head around, like, you know, what is
they're going to roll out an experiment, and they want to use OpenBCI gear, and they want to replicate their results, and that's currently the bottleneck for him.
Cool.
And they're way on track, and they already have something that's mostly packaged. I think they're trying to refine it and get it down to a more core thing that is easier for people to just install Python and do it, I guess.
That's right. Yeah. And then it'd be something that as soon as possible, and, we want to do this over the summer, right? Is you'd be able to put out a call to all of the email lists or all of your, communication channels to people with the devices and say, hey, you want to do a thing? Here's a thing. And it's streamlined, and it's basically like an ERP-based data acquisition thing. Experiment analysis.
And this would make William happy, Joe, because we've seen people in the forums say, I just want to use a neural net to make commands. And we warn against that because it's not been proven in research that you can just throw data at a neural net and that it work. And his comments are usually like, stick with an existing paradigm that papers are. And I've been hearing from the community that good science builds on top of previous science. You don't just come out of left field and throw a Hail Mary. And so that's, I think, the potential benefit to going forward with EEG notebooks is because the science community already agrees on the things that are included, and they even want to reduce that a little more into some ones they really want to do. That's my takeaway.
And that's great. And so yeah, I mean, obviously having the resources to do this will help us move forward, and I'm sure we can work this out. I want to be cognizant of time and to some degree actually follow the agenda that I know I only sent out like an hour before we met. Yeah, so if we can
can we get an email? Just John, it seems like I don't know who else is involved in this. So I think that's what I'm still trying to wrap my head around.
Oh, okay. So Jaden, I mean, that was certainly why, it was great to have you all join today. John's manages the EG Notebooks project and our main branch. And but Jaden's done the work so far to add that in his own GitHub repository, add BrainFlow, which gives us like all this hardware support, the main being all the OpenBCI boards. And yeah, so EEG Notebooks is the kind of all-in-one project that has experimental control and acquisition and to some degree, analysis, all contained in a nice Jupyter Notebook package. And yeah, so in this case, the benefit being that you get all of PsychoPy's, there's some nice pre-canned PsychoPy experiments, auditory and visual that we could run with. And I'm particularly interested with the OpenBCI support because it's easier to get people to have an occipital-like electrode than it is with, say, the Muse, because I would still love to have the steady-state VEP be included. Yeah, so I'm happy to help Joe in terms of getting the right people on an email chain and just working out, the remaining details.
Yeah, I think it's all, like I said, it's all possible. Cool. And I want, John, if your bottleneck is some hardware, we'll work out a loan or a donation to make it possible. And I just want to, for those kinds of things, it's always like, okay, just have to make the case of what is it we're doing? Why are we giving this away? And great. All right. And then it sounds very valuable, and it sounds like it'll be easy to set up. So I think I have John, Jaden, and Chris, and I can kick something off, and I think it'll be easier to just to handle it that way. We'll follow up. I'd probably find another time,
Sure.
working hours for West Coast, East Coast, and then and we'll really like dig into what we can do here.
Sure. And I only saw this Hackaday Prize cerebral palsy challenge I think yesterday. So if that could be a separate thing that is still it reminded me of what your Need Knowers hackathon was going to be focused on in Belgium. So great. Well, thanks, Joe, for joining us this evening. Obviously, hang around if you have time. Gonna shift over to Abigail, and I'll let Abigail introduce herself, but I was super excited to have somebody talking about NERS, trying to make a regular thing that we talk about multiple modalities. And but what I'm particularly excited about here is the computational modeling and that Abigail is bringing to the project, and super important in NERS, and especially when you're looking at different populations, to capture more of the non-neural differences that could be influencing the data analysis. So, but on that, Abigail, turn it over to you.
Wonderful, thanks so much. I can just give a little background about myself, if that
Please.
helps to start out. So my name's Addie. I just graduated from a 4-year biomedical engineering degree at Queen's, which is in Canada, for those of you calling in from the States. And although I did biomedical engineering, I spent almost all my time doing things that were neuro-based. So I started and ran my school's NTX student club for the past 3 years. And I also interned at Muse. So I just kind of took a detour early on more into neuro than engineering, and I'm now here. So in my 4th year, I was taking a biological fluid dynamics course, and 60% of my grade was a course project. So I ended up probably allocating about half of my time overall in first term to just working on that one course's project, because I got very invested in it, and then I ended up turning it into a thesis project with special permissions from my program. So that is what I'm presenting tonight. So basically, my overall project is trying to connect cerebral arterial fluid dynamics to the properties experienced both in blood flow and in the brain. So I'll just figure out how to share my screen quickly, and that way I can walk you guys through my PowerPoint. So let's get this going earlier, but I'm struggling with it now. Can anyone help me out in how to share my screen right now?
So sorry, it's just to the left, bottom left-hand corner.
Yep.
Sorry, I was helping you with my mic muted.
Oh, perfect.
You got it?
Yes, thank you.
Okay, no, cool.
Wonderful. Did it go through?
No.
I'm still seeing you, sorry.
Okay.
So sometimes you have to then select it. It pops up a window, and then you have to select the window that you want. Okay. Yes.
Oh, it went through?
Well,
Amazing.
I'm now seeing.
Sorry about that.
I'm now seeing just a blank screen. We'll get there.
Sorry, I'm trying to troubleshoot this a little bit in the moment.
Sure. So it might have pulled up a screen, and then you have I pulled up a little window, and then you can choose to share your window, or like a Chrome tab, or.
Okay, I'll try and shift it and share my entire screen.
There you go. Or we're
working?
seeing your desktop. Cool. Yeah.
Okay, perfect. Wonderful. Okay, great. I'll run it through then if everything's working well.
Yes,
Lovely.
please.
Okay, so wonderful. So the two main points that I wanted to investigate in this exploration was that I wanted to get a better understanding of the relationship between the physiological vasculature and the neurological measurements, purely to improve collected data. So from working with Muse, I'd worked with a significant amount of EEG data, and I also had investigated NIRS a little bit, and I did not really understand how vasculature played into all of that. So I kind of began my project by investigating that relationship, and then I decided I wanted to investigate it in more detail in order to try and prove the accuracy of the devices. And then my second thought process was I was able to find a lot of theoretical connections between things like blood pressure and hypertension and neurological disorders. And so I was hoping that by theoretically learning a little bit more, it might overall grow knowledge in that category of neurological. So why do we care about neurological disorders? As all of you guys know, they affect hundreds of millions of people globally. Basically, everyone's affected by this to some extent, and it's really important to learn more about. In terms of the relationship between the blood pressure and the neurological disorders, I actually found that there was a lot of bizarre links between arterial blood pressure in terms of the physiological effect on the body. So the first one is I really investigated arterial hypertension a lot, which is just consistent high levels of blood pressure. So in the US, hypertension actually contributes to 1/6 of American deaths, which is a pretty high statistic when you think about it. So arterial hypertension is connected to obesity, old age, stress, lack of physical activity in general, and then regular and significant alcohol consumption. So all things that are generally bad for your health, but also can lead to, if that can lead to neurological disorders, that's something that we should really be looking at for. So this main theory is built in the idea that hypertension damages blood vessels, which can directly contribute to vascular dementia. So it has been shown that it really increases the risk of cognitive impairment. As well, antihypertensive therapy treatments have actually shown to reduce the risk of dementia by up to 55%. So from all of this research, my final hypothesis was that under hypertensive conditions, oxygen flux and volumetric blood flow can actually increase the proportionality to the change in blood pressure. So firstly, I'll walk you guys through my theoretical investigation a little bit, which occurred in the first half of the year before I had entirely changed it into a full year thesis. And then I'll walk you through the empirical investigation, which focused in the second half of the year. So my first question was, how does fluid dynamics and the pulsation of arteries affect cognitive functionality? So after doing a ton of research, I firstly realized that there was not actually that much investigation currently out there on the fluid dynamics of the brain. There's a lot in terms of the aorta from cardiac labs, but there's very little that actually go into the neural investigation of specific fluid dynamics in terms of turbulence and eddies and all of the effects that they can have on your neural functionality. So I kind of wanted to dive more into that, but quickly realized there actually was not even really enough research to get that in depth into it. So I took a step back and took a little bit more general of approach. So these were the 4 main relationships I investigated. So I found theoretical connections between blood pressure, blood velocity, wall shear stress, and oxygen flux. And so decided that I wanted to try and directly connect all of those through my theoretical model and then later empirically. So I relied heavily on the anatomically detailed arterial network model as I wanted to focus specifically on memory loss initially in my theory. So I chose the basilar artery and the posterior cerebral artery. As both of these are very difficult to measure since they are so deep in your brain, I instead relied on a simulated model of blood flow and blood pressure. So as you can see in this diagram over here, the mathematical model had produced exact pressure values throughout an approximated cycle. So this cycle used a 24-year-old male in terms of this analysis. And they, although it was mathematically calculated it, they empirically tested it on easier to test body parts such as your wrist and your ankles to ensure that it was accurate. So I trusted that they'd done a pretty good job and took these values right here for my initial model. However, if you had MPUs, you could also put those in, it would theoretically work out. So my model specifications for my theoretical model are that I conducted Fourier analyses on the data, and I also tried to generate a pulsatile flow. So I tried to model the extent of the cerebral arteries as a function of the one-dimensional pressure going through the artery of the blood. So throughout a heartbeat cycle, I track the pressure on the wall of the systole and diastole. So these are some of my results. So one of the things I chose to calculate was the wall shear stress, as that is proportional to oxygen. So I used it as the measurement system in my theoretical model. And so as you can see here, I chose to use pressure values for normal conditions as well as hypertension conditions to try and test out my theory of arterial hypertension. I also was able to track the velocity as a function of radius, which I found to be kind of different, as you can see the different effects of the actual blood flowing through the artery as a function of the radius. So this top one here is 0.12, where the bottom one here is 0.08, and the only thing changing are the radiuses. So this is just kind of a quick example of the reason we need to investigate fluid dynamics when considering these variables. I also, sorry, I'm gonna make this full screen. So as you can see, I also modeled the velocity field over time for the hypertensive and normal conditions. As you can see in these GIFs I created, you can actually watch the velocity changing over time of the cycle. And this is for the basilar artery specific context, but you can enter in any artery as long as you have the values using the Aiden model. So now I'll move a bit more into my experimental investigation. So I followed this classical of I designed an experiment and I used a software package to interpret and analyze the data. And then I tested the software package using test data. I recruited participants and then I collected data and then I drew conclusions from the graphical trends. Unfortunately, COVID happened at the point where I was in between recruiting participants and collecting the data, so I was not able to completely finish this, but I'll get more into that in a minute. So my planned experiment was a motor imagery experiment and a motor execution experiment. Very simple. The participant would just be sitting at their computer and there would be stimulus arrows either gesturing to the right or the left or nothing. And I just took quick 10-second chunks after each stimulus occurred in order to play around with the data a bit. So the devices that I used in this test are I used an FNIR system, a blood pressure cuff, and a PPG sensor. And I aimed for 20 males between the ages of 19 to 22 to mimic the Aiden model. I also used light-skinned males for the FNIR system, just so that way I would not have to account for the skin index value. Finally, I wanted to measure blood pressure, but I didn't quite trust the finger PPG sensor or the blood pressure cuff as I was readings. So instead I use both.
Sorry, Abigail. Photoplethysmography.
Yes.
What is that?
That should just be PPG.
PPG, but that's a. I mean, how does that differ as a measurement? Sorry.
Sorry, as a measurement from the FNIR system?
Yeah.
For that measurement, I actually put it directly on the participant's finger.
Okay, so is that like a pulse ox?
Yes.
Yeah. Okay, sorry.
Yeah, it's exactly that.
Gotcha. Sorry. Thank you. No.
Yeah, so the measurement techniques I used were first I used an FNIR system, so I just relied on the Oxymon Artemis equipment. It was just a very simple 20 channel on each side, which I got the participant to wear. However, I did not collect EEG data as well. I just and then I used the blood pressure cuff, which is just a simple cuff that goes on the person's bicep, in the EEG sensor, which is just a pulse ox and goes on the person's finger. And together, the EEG and the blood pressure cuff just gave me relative blood pressure data that I could use. So as I mentioned a little bit earlier, COVID happened in the middle of my testing process, so I was actually not able to complete testing. So I only got about 5 participants before I got cut off. So instead, what I did was I used my last 2 months of my project to flush out pretty intensive MATLAB libraries for an analysis for this experiment. So I just kind of really dove into doing FNIR's analysis with my libraries. So I can walk you through a little bit about what those are, because all of those are open source, and I really think that they'd be useful to cut down on some time for anyone else that's kind of playing around with this stuff. So my feature functions that I developed in the library were signal processing for all involved measurement devices. And then for the pulse ox in the finger specifically, I did calculations for peak to peak, heart rate, and then I did all the derivatives that could be relevant. For the FNIRs, I did basic filtering and signal processing. And then for analysis, I did analysis of each individual test result, as well as state comparisons for the motor imagery and motor execution, action comparisons for the left stimulus, the right stimulus, and the left stimulus, or the stimulus, sorry. And then did participant comparison and motor execution, which pressure and oxygenation percentage as consideration values in terms of trend comparison. And finally, I considered the continuous blood pressure value and the oxygen percentage values. So here's just some of the figures I was able to produce to give you an idea of what it looks like. So this is really messy with all of my channels. But then I was able to produce nicer things like this, which actually produce pretty nice qualitative trends for just test data, which gave me some confidence that this could actually work if I was able to go full out with this experiment, as well as other things like this for easy qualitative analysis, where this one specifically represents the blood volume levels, and then each different participant is recorded and labeled here in terms of their blood pressure. So you can actually see a pretty strong trend with the 110/70 blood volume values just consistently being higher with blood volume, which is why it's positive. And then as well, there's just some more trend comparisons. And then this is a PPG sensor, so I was able to create an algorithm to identify all the local peaks. So that is the local maximum systolic pressure. So you can use this in terms of heart rate calculations or HRV, which is heart rate variability, sorry. And then I also had continuous blood pressure, which is with the finger sensor. This one was not great. However, it was the best one that I got, because every time I put it on, I was playing with it, because I didn't really realize that we had limited trial opportunities. And then here are a few of the references I used. I have about 2 or 3 pages in my actual thesis, but this is just a couple of the main ones. And that is it.
That is great. Thank you so much, Abigail. I put links in the chat to your GitHub. And can you say, so what you were showing us, is that the FNIR analysis, or is that the neural field dynamic project? Like, what are the differences between those two?
So the first project was the initial theoretical analysis that I did, where I used the simulated values. And then after I kind of did all of that and I saw direct trends in the theory that I calculated, I then dove into the more empirical process, which was the FNIR specific. However, they are both separate MATLAB libraries, or one MATLAB model and then MATLAB library.
Gotcha. And well, so does anybody have questions for Abigail? I don't know if did Kyle join us?
Yeah, I came a little late. Sorry, but I caught the second half.
Sure.
Cool, Abigail. Maybe my questions you already answered, but how do you like place the sensors on the people, or how do you know where?
So we had an EEG cap, and then we just attached the FNIRs to the EEG cap, and then connected that to the Oxymon Artemis system.
Got it. Okay. Cool.
I have a question for Abby. When you measure the PPG, do you calibrate it with a normal pressure cuff?
Yes. So in this measurement, I actually put the cuff on the person as well as the PPG to make sure that there was no improper shift by removing the cuff. So I took cuff measurements both before and after the experiment.
Gotcha.
Hi, I have a question. This is Suhas. I'm sorry for asking a dumb question because I joined late. The goal was to see if hypertension would affect memory, or what was the hypothesis you were looking at?
Yeah,
Okay.
sorry about that. So the ultimate is just trying to draw connections between hypertension and the blood flow that we were able to measure in the brain. So it was kind of twofold. One, I was just kind of curious and wanted to see if I could produce that, because there'd been some research connecting it theoretically, but not that much. So it was kind of a new area I could explore. And then I also, there was a lot of research that if you connect it all, it kind of hints that there could be connections between hypertension and neurological disorder. So I want to investigate that and try and play around with this model.
Okay, and this was sort of building up the model because I imagine there's not a lot of hypertension in 19 to 22. Okay, all right, makes sense. All right. Although maybe you could induce it with some, pharmacological, but yeah.
Did you consider the implications in migraines?
Yes. So that was one of the main things was I get very bad migraines. I found that at school, both my friend and I were stressed, our blood pressure would increase and we would get migraines.
Can I say something? Like I think some people with severe migraines, apart from using triptan class drugs, which are very, very specific, I thought they're also being prescribed medication that regulates blood pressure around the whole body, and that ends up, that's why I was talking to Morgan. I was very excited to hear this talk because blood pressure is very important. That's why when you go to the hospital, they check your blood pressure and they check your temperature. Two very, very strong metrics.
Definitely. And I also found a lot of really interesting statistics connecting them. For example, a lot of the symptoms of hypertension are actually neurological. So there's relative migraines and headaches, as people can and have longer lasting terms, which are definitely some sort of neurological connection. In addition, with antihypertensive treatment, the odds of someone getting dementia actually decreased by 55%.
Yeah.
That's cool.
So certainly, one of my first, introductions to computational modeling of FNIRs was Solomon Diamond I think it's like a 2008, paper. And, what he was really showing was that like, the best way to do FNIRS is also to have like a strain gauge for the chest, and, pulse ox, blood pressure, and to be capturing all those, systems, and then including that in your modeling so that what you're drawing from the FNIRS is really as much as possible neural based changes, and so yeah, I think this is a great start to the way people should be doing or tackling their FNIRS data. Yeah, so I know I see John in the comments bringing up vascular field dynamics from all the discussions that we talked a little bit about this in terms of fMRI is echoplanar imaging and blood level oxygenation dependent effects, and that is a kind of a muddy measure. And there are these other ways of with fMRI capturing cerebral blood flow and blood volume with ASL and vaso, and yeah, that a lot of that or some of that data is publicly available to play with. So I don't know if John, you want to say anything more about what's current in these kinds of I can think of lots of, I was in particular thinking of like Dan Handwerker's stuff in terms of aging effects in fMRI and needing to control for older subjects vasculature and also differences in just in their breathing.
Yeah. There's a there's a couple of areas where it applies, and they have different emphases. And at one level, like everything to do with the bold signal is somewhat influenced by vascular dynamics. It is kind of trivially obvious, but it's also it's something that just it kind of raises its head in various ways, and as confounds of various types in kind of signals with fMRI. For example, as Morgan was saying, like individual differences in disease effects in vascular properties, right? That's something that isn't really controlled for. It's not even clear that it's possible to control for, but it's also like differences in brain regions and just their vascular properties, something that's known but isn't really properly accounted for in statistical methods. There are people, the Buxton model for the bold signal, which is like the main model that's, let's say the main model that's used to calculate hemodynamic response, the hemodynamic response function, like the biophysical model, is it's a fluid dynamics PDE, big fat nonlinear PDE that's pretty hairy. So there's all kinds of fluid dynamics, like vascular fluid dynamics, that at various points in fMRI, and some of them are more like the balloon model. That's like full on fluid dynamics, really thinking about blood flow and vasodilation and how those things kind of interact over time. Some of the similar these confound things, they tend to be kind of more signal processing challenges. The thing that I put in the link there is something slightly different, which is to do with traveling waves of hemodynamic responses. And it's kind of like a traveling wave that flows through the capillary networks. So it's something, it's still fluid dynamics, but it's fluid dynamics at a slightly kind of more macro scale than within an artery or within a vein or within a capillary per se. It's like through a capillary network as a kind of traveling wavefront. And when you get to that level, you're kind of down, you're at this murky area where the structure of the vasculature is kind of around about the same scale as the structure of the functional organization of the cortex. And that's really hairy territory, because generally with fMRI, what you like to be, you like to think that what you're looking at is the brain's functional specialization in terms of its, this is the way that representations are laid out, and information processing is laid out. And you think about that as like the organization of, networks and hierarchical functional systems in cortical circuits. But you get down to the level of, the level of cubic millimeters, or just under the level of cubic millimeters, and like the vasculature is as much of a structural feature as the actual functional organization. So that's an interesting challenge that people who do high resolution fMRI, like my friend Kevin Aquino, who's the guy who I put the link in there, he works on this kind of interesting combination of high resolution fMRI in the visual cortex, and some of these problems. So some of these, research questions around characterizing the hemodynamics and the kind of traveling wave fluid dynamic aspects of the hemodynamics. And they're actually quite a nice pair of things to be looking at, because you're faced with those challenges when you're looking at fMRI at that scale. I mean, you're also faced with a challenge, I should say, of at a macro scale in terms of things like the kind of signal properties of major draining veins and so on. So it's not just at the sub-millimeter scale where the microvasculature influences what you're seeing. There's like macrovascular properties that really affect like the type of signal that you're going to see in the medial temporal lobe versus the lateral occipital lobe, for example. But the microvascular things are more interesting from the point of view of fluid dynamics.
That's
I
really
could go on, but I won't.
No, I mean, yeah, I think, or certainly, sorry, I let Abigail. Do you have questions?
No, that sounds great. It's just really interesting. We're excited to go read all these articles.
I mean, and so currently, Abigail is I think working for a finance company, but we are trying to bring her back to the side of light and hope. And so I was pointing out that there is a lot of there's a lot of good fMRI data, but I love that fNIRS is such a more accessible technology to, and as Josh has shown us, like we can make very low cost systems that collect data that is very fMRI like. And so we can be dealing with what are the real problems is the computational modeling. And what I would love, I know you didn't, and you probably won't be able to get back in the lab very soon, but what if you did have EEG on those same subjects? And I mean, I know this was a homogeneous sample, so you didn't have 20-year-olds and 80-year-olds, but looking at the EEG NIRS of those, say those two groups, and being able to have the EEG to basically see how your computational modeling of the NIRS is doing in terms of removing those non-neural sources influences, and how well can NIRS actually give you that a sense of the electrical measures from the joint. That would be, and it comes up in other things than just hypertension. I mean, if there are patient groups that are taking one, or in psychiatric cases, multiple drugs, that many of which also have vasculature effects, and we're plenty of studies are looking at trying to do fMRI of those. So I love to see this more of this computational work, and just will point out, since Michael's not here to join us, but that there is that MOAB or that data set that's included in MOAB. It's a motor imagery data set. It has the NeurotechX multi-channel NIRS and EEG. And because it's NeurotechX, you can read it into M&E. So it's another data set that love to see people using, especially for this kind of joint analysis. Yeah. Other more questions for Abigail?
I had another question.
Yeah.
I think there's a study that said, like, if your necktie is too tight, it affects your cognition. Have you ever? Do you want to do something like that with your 19 to 22-year-olds?
So that's actually how I originally started thinking about this. Was I read a study about how, well, first I was thinking about the pulsatile required motion of arteries, and then I was thinking about restricting arteries and how that would affect blood flow as well as the oxygen flux through the artery to the cells. And then I found a couple studies that said if your neck gets restricted, the blood flow to your brain is obviously affected. And so it changes the properties of the fluid dynamics in your brain and therefore changes the oxygen flux through the arterial wall. So there's a whole bunch of really interesting areas around there, such as when you get older, your bones and your muscles and everything naturally restrict. I wonder if like keeping your neck more limber, or even something simple like that, would be able to help reduce the effects of aging in your brain. So I feel like there's a ton of research and interesting investigations to be conducted around all of that.
When I did really like DCI, I don't know if any of y'all know what that is, but we had a yoga trainer, and part of the yoga stuff and doing exercises is getting blood flow to the rest of your body. So, I mean, and also you said like constricting the neck reduces blood flow. I think a lot of bad guys are saying, I told you so. Because people have, But can you speak on any more into what you wanted to see in regards to migraines about your study?
Oh, yeah. So a lot of my brainstorming, once I switched to empirical, since I am using only 19 to 22-year-olds, I was trying to think about how to induce hypertension of some sort. So I was trying to figure out ways to measure.
They have intravenous drugs for that, but I don't know if you want to go that route.
Yeah, I didn't even consider that as a thing I'd have access to as an undergraduate thesis, but that could definitely be an interesting area to explore going forwards. Yeah, my main thought process was to have people that do get migraines, like fairly regularly, hopefully, come in the course of a school term if they're in university, for example, as you can kind of assume that their stress levels are going to be heavily increasing, and trying to somehow quantitatively measure that over the course of a term. I was really just spitballing and trying to check a whole bunch of boxes and inducing hypertension naturally in these young people. But yeah, I was kind of hoping that people who exhibited migraine symptoms would be more likely to have both hypertension and those faults.
So I seem to be called out for some audiovisual difficulties, but yeah. Again, thanks so much. Hopefully, we'll. I know you're. Yeah, I think you're also applying to grad school right now, and so. I know you're if there's advice or other things that you are looking for, please let people know. and certainly posted your GitHub projects. Just one second, let me handle some technical problems in the other room.
Yeah, definitely. So I'm currently applying for grad programs. I'm applying for a range of master's and PhD programs. Everyone I've talked to has had a different opinion of where I should go and what labs I should aim for and whether I should do master's or PhD. So I'm kind of collecting them if anyone feels like steering me in a direction.
What's your inclinations?
I think I want to do something neurological disorders based. Obviously in neuro to some sort. So far I'm looking at mostly clinical neuroscience programs, but I really like the coding aspect of it. Yeah, I'm kind of just trying to see. Right now my main application places are UCL and then a bunch of Sweden states.
I don't know how big it's gotten, but our school actually just opened up a brain health PhD program in neuroscience that they're doing in conjunction with the Lou Ruvo Center for Brain Health, and I believe they're an offshoot of the Mayo Clinic. So might be worth looking into. They're I think next semester is going to be the first semester of the PhD program.
Wow, that's very cool. What school did you say you went to again? Sorry.
University of Nevada, Las Vegas.
Okay, cool. Very interesting.
You said UCL, right?
Yes.
Yeah, so they do this 4-year PhD program, the Welcome program. Is that one that's you've been looking at? There you go. This is actually, neuroscience, physiology, pharmacology. It's one of their flagship PhD programs. I tried to get into that about 15 years ago. They wouldn't have me. But that's a really great program. UCL's top brass place. You can't go wrong with the Institute of Neurology there. And if you want to do neuroimaging, that's the center of the universe for neuroimaging still. If anyone cares to challenge that, I'd be interested to hear. But
what's the nicest thing they have? Can you educate me? That's if they are on the forefront. What are they doing? Special MRI. 5D
all right, so
something?
it's okay. It's a little bit right. I guess it's kind of history as much as anything else, but there's a few analysis methods in neuroimaging that came out of the methods group in UCL. So there's a tool called SPM, which stands for statistical parametric mapping, which is still to some extent the methodology there is called mass univariate statistical analysis, basically. But the general idea and the primary software tool that's used in the field still, it's a bit more heterogeneous than it was a few years ago, but it came out of the group that is referred to as the PHIL, the Functional Imaging Laboratory, but they've not actually been called that for about 10 years. They're called the Wellcome Center for Neuroimaging. So those guys innovated on a lot of the statistical analysis methods for functional neuroimaging in the kind of end of the 90s. And then in the 2000s, they developed these methodologies for physiological, let's say network modeling of neuroimaging data. The main guy is Carl Friston, who's the most highly cited neuroscientist in the world, and has Wired articles written about him because he's very smart.
Can someone type that name? I haven't heard it.
Sure.
Yeah, sure. Yeah. Let's find the Wired article.
So I'm looking at the SPM page, and I see these what I know as typical images of active areas in an MRI scan, and you're telling me they basically made the algorithms for that. Yeah.
They they made like the software tool and a lot of the algorithms that are the ones that are basically what the field uses.
There's some other packages too.
Some other ones, yeah. What else?
Like
oh right, yeah, no. So yeah, I don't want to say, but if you look at the statistics, right, of like in neuroimaging, it's like SPM 80%, or at least 5 years ago it was SPM 80%. And it's like FSL, free surfer. I think that's kind of reduced down, but it really is like the dominant like tool that's used in neuroimaging still. But that's not the interesting stuff. I mean, that was, and also voxel-based morphometry, which is like a structural imaging analysis thing. But that's kind of history. The more interesting stuff is the physiological modeling stuff that group like spearheaded with dynamic causal modeling and its kind of associated things. And then Carl Friston has the whole free energy principle theory of everything, which is having a lot of influence in in machine learning and in theoretical biology and a bunch of different fields.
Yeah.
And there's other interesting stuff. Oh, okay, other stuff in at UCL as well. There's the microstructure imaging group. So Daniel Alexander is the guy who leads that group, and they do really cool, basically diffusion-based white matter and gray matter microstructure imaging with MRI. Loads of good people at UCL.
Yeah, I mean, it's biomedical engineering as well. I mean, in terms of, yeah, I mean, there's NIRS groups, there's EIT groups, there's, and certainly, in particular, neurology is all centered around Green Square. So you have, multiple neurological institutes and associated applications groups all centered in this one particular area of campus.
Yeah, it's a cool part of London as well. It's right around the corner from South Ken and the British Museum and King's Cross. I love it around Queen Square.
Yeah. So, and there by the way, there is also there's an FNIRS version of SPM. So you can use SPM for your FNIRS, at least, yeah. So I've heard, and so I'd been following up this weekend with David Boaz about Ninjaneers, and their openfnirs.org site is really great in terms of listing other software packages that. Some of which I hadn't heard of. So yeah, I don't know if I've got any more. Kyle, did you want to say anything in terms of the kinds of necessary, physiological confounds that go into an analysis pipeline for FNIRS? I'm on the spot, but so maybe later.
Definitely go snag him.
Well, really great, Abby. Thank you so much. And yeah, I hope you're able to maybe continue doing some of this as soon as possible. So yeah,
Wonderful.
sorry. Any last?
Thank you so much, everyone, for listening to me and giving me advice on schools and everything like that. It's great. I really appreciate it.
Cool. So, and I did drop in. I don't know if I dropped that Solomon Diamond paper in the EEG FNIRS is in the chat too. So, okay, well, so moving on to brain training, and so some of you might have already seen this presentation before, but I wanted to give Suhas a chance to go through this with us, and we had some technical problems before.
This is actually part 2 of the presentation.
Okay.
The first presentation was about behavioral changes, and then this is about the EEG changes.
Okay.
So let me, how do I share my screen? Okay.
So yeah, just the bottom left-hand corner.
Okay. Okay, can you guys see my PDF?
Yeah, yeah. You can full screen that.
EEG-derived changes in brain activation and network connectivity in corporate employees due to brain training. And this is work I did at what used to be called Platypus Institute. It's now called Optios. So just as a rehash, let me just zoom in a little bit. 22 employees, half male, half female, middle to upper age, some youngers. Were doing brain training. And so we did what's called the Dana Standard Battery with EEG. Before brain training, we had them do 6 weeks of training, and then we did the same Dana test after the 6 weeks of training. The training comes from a company called Brain HQ, also known as Posit Science. And this, just as a little bit of motivation, these corporate employees come from Fujitsu. Fujitsu is a Japanese company. Japan, like much of Asia, is aging rapidly, and so they want to maximize the health and productivity of their employees in a number of dimensions. So that's why Fujitsu was interested in doing this study with Optios. So this is what the data collection looks like. We did the Cognionics Q20 dry electrode headset, and then subjects were doing the tablet-based data test here, and then all of their responses get saved and then uploaded to the cloud, and then this all gets saved to the laptop. They weren't looking at this laptop. This was just a picture for this, just to show other people. And then the Dana assessment is composed of 6 tasks, which measure things like reaction time, decision-making, spatial processing, memory. And then a nice feature is it repeats the same task before, at the beginning and at the end. And so you can measure, what do you call it? Brain fatigue or down. But some people actually went up. So it was like they needed some time to get their brains warmed up. There's no real practice effects from doing this sort of reaction time task. So even though you may have did it here and then you did this later, 30, 40 minutes later, it's not like you remember the task and now you're doing it faster. It's something interesting was going on with some people. Any questions on the task rather? No. Okay. Yeah. And then another nice feature is this is Dana was collected on something like 400 military individuals, and it's also used it's FDA cleared, used in clinical populations. And
that was my first thing. I looked up Dana and I was like, this is for defense.
Yeah.
But I guess does it involve things like people in military? No, I guess it was just used by them.
So yeah, the military initially paid for this development, and there's this sort of go no go task where you have to zap or not zap a target. So, but zapping and not zapping, inhibition of motor response happens in fields outside of the military. So yeah, this is sufficiently general that you can test it with military, non-military, sports people, aging people, populations, and so on. Yeah. Okay, so the goal was subjects were told to do 20 30-minute sessions over 6 weeks, and then they could do that on their laptop, tablet, etc. And then we had, again, 22 subjects. We did a median split. You guys see my icons blinking up here? Is that weird? I wonder if this has to do with the presentation, because my icons up here are blinking. Oh, well. Okay, it's just on me. So 22 people, and then we just, rather than doing randomized control, because there was a small number and because of the sponsor, we just did a median split on the subjects, and that created two groups, a long training group and a short training group. A long training group, I think, trained about 7 hours on average. Sorry, it's roughly 2x. I don't remember the numbers. Maybe they'll come up later. But here's a little bit more about the EEG processing. We were looking at regions of interest in the cognitive control network as a function of training and as a function of training dosage. And then I will only show you statistically significant changes. Also did spectral analysis at the electrode level, and then computed ratios. And then just as a gross measure, we just averaged over all electrodes, all bands, and all tasks to give some sort of like a brain power index. And finally, we also used, or in addition, we also used this EEG workload, which comes out of work from NASA. And they had people doing sort of in a flight simulator, and they would increase the cognitive load, and lo and behold, this ratio would go up when the cognitive load also went up. This is a little bit more about the EEG preprocessing. This is basically the prep paper. To do basically common average referencing, and then bandpass filtering and removing artifacts and other things. And then once you do that, of course, you can compute band power and ratios thereof and other statistics. And then the sort of more interesting part comes of source localization and flow, which is both S-Loretta, which is source localization, and then Granger causal information flow modeling. And I can come back to that in a little bit if there's more questions there. So these are the behavioral results, which I talked about last time. There was, both groups increased as a function of training. That's what these pound signs are, at least on many of the tasks. But on a couple of the tasks, there was a dissociation, this PRT and GNG. There was, both groups increased, but the long training group increased more than the short training group. And these are sort of decision-making tasks, so that's kind of interesting. We didn't see that many change, or as we didn't see that same effect on, like, a spatial processing task or a reaction time task or a memory task. So that's good. That's interesting. Yeah. Any questions so far? Okay. Can you guys see the poster? Shall I zoom in?
We can see if you full screen, you'd get a little bit of extra real estate.
Okay.
I don't know if you'll then lose your zooming, but
yeah, it looks like okay, I'll just zoom in further. Got that. Okie schmokes. Brain networks. Okay, so as we know, there's many brain networks: cognitive control, attention, and the default mode network. This is especially important. Or you see a lot of changes in this network due to depression or PTSD. But cognitive control is the one we were especially focused on because of the decision-making tasks that showed a dissociation in the groups. So this comes out of work from Williams. There's 12 ROIs, 6 on each hemisphere, which are part of the cognitive control network. Dorsal parietal cortex, precentral cortex, DLPFC, and ACC. And I guess I'm missing another one, but can't remember off the top of my head. Okay, so this is what, so actually this actually turns out to be a lot of data. There's 12 regions and they're each talking to each other. And then there's the forward and the backward. And then there's the before and the after, and then there's the long training group and the short training group. So even if you look at one brain, you're talking about 12 times 12 times 5 times 2 times 2 data points. So it's actually quite difficult to like look at this data and be like, what's going on here? Where are the patterns? So because at least I have difficulty, visualizing 2000 dimensional space. But if you guys have any tricks or tips, please let me know. Anyway, this is what their brain networks looked like before brain training. Not sure you can really tell much from this, but it's pretty. So anyways, over here, I just focused on the a couple of things. One is high frequency bands, and two is this interesting area known as ACC, anterior cingulate cortex. ACC is important and plays a role in conflict monitoring, error detection, and the like. So it was interesting to look at this. This sort of fell out of the data, but it was also part of me looking at that. Like, if I found something interesting in just in inferior parietal cortex, it's like, oh, that's interesting, but that's not really what we're after. We're really after changes in more prefrontal areas. So what we saw was that in the long training group, ACC decreased its connections to posterior cortex. And here, blue is a decrease in the connection. So you'll see a decrease in alpha and a gamma. But in the short training group, there was actually increases in the from posterior cortex to from posterior to anterior regions. So that to me was kind of interesting. It was at first kind of what is it, counterintuitive, right? So if you're using more cognitive control, then you would expect this network to increase in strength. But in fact, it was decreasing in strength with the long training group. So I think there's at least two possible explanations for that. One, as we saw in their behavioral results, the long training group had better performance, less error, less conflict. So in that sense, ACC is being used less. So maybe that's why the connection is decreased. Another reason would be, that the decision making was becoming more proceduralized and shifted away from deliberate areas in the front of the cortex and pushed into posterior or subcortical regions. If you guys have any other explanations or thoughts, please let me know. Yeah. Can you guys also see my mouse?
Yeah.
Oh, okay, great. Cool. Okay, so that was the brain network analysis, and I can go into a little more detail of that. It uses a package called SIFT from the UCSD Schwartz Computational Neuroscience Center. Really good, really cool software. It is a little bit of like, searching looking for your keys where the lights are, but it's also powerful and interesting. Okay. So now I just want to talk about some spectral analysis. And okay, so there was a change in this overall brain power index, which is interesting, but there was also a change in this workload measure. So before brain training, the long training group and the short training group looks similar, a lot of activity in the frontal cortices and this less activity in the posterior cortex. After brain training, you can see the long training group is sort of working less The frontal regions are used less, but perhaps the posterior regions are used more. This was dark blue, and now it's light blue. So maybe that's support to the proceduralization hypothesis. In contrast, the short training group is almost working harder. And maybe that's, because they're making more mistakes, or even though they are doing better than before, their brains just haven't hit that low energy state. And you'll see actually increases in these, in all of these areas. But at least their behavior was better. Behavioral performance was better. So that's what I wanted to say about the EEG. And so overall, I think we showed a positive benefits from brain training. And so we showed changes, especially in decision-making tasks as a function of a dose. And we actually showed changes in the functional brain network with EEG. Nice thing about EEG, as we all know, is it's cheap. And, especially if you're a cash-strapped startup, you don't have time or money to recruit a lot of subjects and put them through MRIs and the like. So this was nice to use SIFT and to measure and detect changes in brain networks. So that's pretty much it. That's what I wanted to share. I'd love to hear your feedback or comments, criticisms, other explanations.
Yeah, well, thanks so much, Suhas. So, certainly the problems that you have with doing this kind of brain network analysis, especially with cognitive tasks, is like you said, like how you're going to see a lot of activity in a lot of places. And how to put together a set of networks and be able to distinguish some real some real changes in the task relevant areas. So I mean this is certainly one of the issues. We talked about dynamic causal modeling earlier, and one of the one of the first stages of DCM is like deciding basically what network you're going to look at, and kind of how you're going to get to that, whether you're going to take your, I mean, did you took your S. Loretta results and thresholded them in some fashion, or can you lead me through that bit?
Yeah. So I'm mostly forgotten the details, but yeah, these are statistically significant changes. But you're asking for more.
Well, I mean, so that could be the first stage, right? So the question you get if you use a source imaging to get whole brain results, right? And using some appropriate multiple comparison correction, and then you have to make this decision, or certainly this comes into DCM, which I think is totally relevant if you're going to do kind of Granger causality as well, right? Which is well, okay, so that gives me a bunch of blobs.
Yep.
Do I really want to use all these blobs in my network analysis?
Yep.
Right. And again, I not so much about the neuroimaging, but more about the Granger causality is, I think the DCM, like I forget the title, but it's like 10 rules for DCM analysis or something like that. It is still a good checklist. And yeah, so I mean, do you remember if you kept all your blobs? Did you take a subset of those and say like, well, these are areas that are typically linked together? And
these are a
yeah.
priori ROIs, right?
Yeah, that's right. So we picked 12 regions, and
okay.
yes. So that's actually I would as like DCM is like both under constrained and over constrained. So it's like this weird mystery. What's really going? Parts that I didn't like about this is like you have to pick your regions a priori to get things to go fast. So then you're really only looking for your keys where the lights are. And then this is like measuring information flow between these 12 regions, but it's like, well, this might say over here, hey, you know what? 90% of the network activity is between DLPFC and ACC. Well, no, 90% of the activity of these 12 regions is between DLPFC and ACC. It could be that DLPFC is primarily talking to some other, subcortical structure, who knows what.
Sure.
So it's like I'm a little unhappy with that, but at the same time, if you just throw everything in there, not only are you now you're not dealing with a 3,000 dimensional space like I was alluding to before. You're dealing with a much larger space, and then
sure.
then you get into well, you're going to find I don't know if you guys see that paper, but they like put a salmon head into the fMRI machine to calibrate it, and they're like, oh my gosh, look at this. If you take off all the model constraints, you can find voodoo correlations. So I don't know what I don't know how to what the sweet spot is. Is it 12 regions? Is it 4 regions? Is it 40 regions? If you guys know, please let me know. So yeah.
I think this is a good number for EEG and MEG. What did you have, like about 12?
Yes, yeah.
Because really it depends obviously what the structure of your data is, but the dimensionality of EEG and MEG data is much lower than the number of channels. And when you're talking about looking for any of these statistical techniques that are trying to identify something from correlation structure, right? Covariance structure, which is what Granger is, and it's what the source reconstructions are doing. So the source reconstruction is based on the covariance structure of the signal, right? The connectivity analysis is based on the covariance structure of a signal, like it's maybe a derived signal, but it's ultimately like covariance structure of the data. And the number of the dimensionality. So, if you're looking for more, if you're under conditioned in terms of looking for relationships between independent sources of variance in your data, then you don't want to have 120 region parcellation and do connectivity analysis on that in source space with EEG and MEG, because you've only got like 30 independent rows in your covariance matrix. So I feel my kind of sense is that the number that you've gone for here is probably about the sweet spot. And I think that, if you look at, say, Mark Woolrich's stuff and, Mark Woolrich's group, the guys in Oxford, they're kind of the leading people really in MEG at the moment. Like they do all their stuff on parcellations that are around about 30 regions.
Okay.
But that's with MEG, which has a lot more channels.
Yeah.
And typically, DCM models, rarely get outside of double digits in terms of the number of nodes.
Yeah. But that's for a different reason. That's because then the number of parameters in the models, not exact. It's not. There's more parameters in those models than just the network structure. There's other parameters, so it's like.
Yeah. I still like the interpretability and the mechanism for deciding on which model is there the best evidence for in DCM, as opposed to these, like thresholded Granger kind of maps.
Right.
But I mean, it's pulling out these networks is still hard in EEG, or pulling out meaningful networks and interpretable results of those kinds of that kind of modeling is definitely hard to do. I forget, this was 20 channel EEG, Suhas?
Yes, that's right.
Yeah. Well, I saw your Slack question. I don't know if you got any answers on that in terms of other list of companies that are doing brain training plus BCI. But I'd still love to see even a preliminary list, because you're more in that space, familiar with some of the big players. I'd still love to see a short list that could get others started.
Yeah, I'm. It's not something I want to do, so right now I'm
I think I lost.
Ultimately produce some sort of, maybe like a Gartner type report where you have axes. These are the this dimension is I don't know, cost versus performance, and this dimension is invasiveness versus something, or privacy versus. Anyway, yeah. Of course, there's never enough hours in the day, so something I'd like to do.
All right. Well, thank you. If there are no more questions, I just want to thank you again for your time, and I didn't actually ask if there was anybody new here who wanted to introduce themselves. I know that there was a few people in the beginning. So yeah, in terms of has anybody been following NiLearn Dev Days? So,
I did the first one.
Yeah, all the talks.
Yeah.
Yeah. I mean, good stuff. And
have you been on the other ones as well?
I got sucked into all sorts of things yesterday and today that were not on my schedule. So I have not, but I really wanted to. Yeah, I mean, I also saw the Brain Age paper. Did you see that from MEG plus? Yeah. So another paper from I think Gail's the last author. Is it Denny Engelman? Yeah. Anyway, I can try and find that, but it seemed like everybody's with Vince Calhoun doing the Brain Age Kaggle competition. Everybody's coming out with Brain Age results. I still think that's really cool, but even better if you can derive it from sleep EEG like Boston has. In terms of being a much more cost-effective way to get at that, and what they've shown in terms of the reliability of sleep EEG. So doing multiple recordings over many nights, and getting consistent brain age results. Do you know
Is
those?
that? No, I'm not familiar with that.
Yeah, I will find that, and I want to say that's I know it's MGH, but give me one sec. I think I saw their most recent archive, but the archive. Yeah, but that was actually focused on the reproducibility. Like this was like a 2018 paper that has already been published that first showed this. Just a second.
We just got a grant approved, small one, to do some sleep EEG.
Oh, cool.
Modeling and analysis stuff. With
Okay.
Steve Mann. So.
Oh, nice.
Doing some Muse-S sleep stuff and doing some physiological modeling around that. So I have to buff up on sleep, which I'm interested in. So that's cool, but I have a lot of reading to do now.
Hey, Suhas, I have a question before you go.
Yes.
So just to put your paper in a nutshell, I can ask the questions now that I can see the whole paper. Did you consider that maybe even with the Dana test that the first time you do it, you'll make more mistakes, and then just even not the training itself, but they get better at the assessment? Like I know you had an assessment, you had assessment training and then assessment again, but even if you take out the training, I guess
6 weeks.
I guess you said you didn't have a control group that didn't have any training, and they just took the assessment. And if they take the assessment 10 times, they're going to get better.
Yeah, so the assessment and the training are different. So that's so that's showing some generalization. So the improvements that the day-to-day variability and test retest, that delta is smaller than the deltas we saw from training. Yeah, that's a very small delta.
Oh, okay. So it didn't. Y'all accounted for that. Cool. So, just to summarize it, brain training is good for both short and long term, but you saw a unique effect in the long term training.
Yeah, more is better, but it's but it's to be honest, the brain training is kind of boring.
The one I'm familiar with is called a double in back. It's not very fun and it's kind of hard.
Yeah, double end back. I hate that one. But these are sort of simpler video games that you can play on your cell phone, etc. What was my point in saying that? I don't remember. Maybe I need more brain training to keep up my working memory. But yeah.
Well, cool. Thank you for sharing.
Thank you.
So I posted that first paper. So that's the 2018, and I'm just trying to remember what the it was like. This is the annoying thing about Slack is that I posted this paper in Slack, and now it's no longer it's gone down the Slack memory hole. So I want to say that it's called like night to night variability. I'm not just getting it from sleep variability. Yeah. Yeah, here we go. Yeah, night to night variability of sleep. encephalography, brain age measurements. So it's the same Brandon Westover at, I guess that's Children's. Well,
so people are looking at this epilepsy data set and then picking up brain age stats. Is that the context?
No. So that is originally what I was proposing from the larger TUH data. So when I originally posted this on Slack, I was like, look, with what this group is showing, there is enough sleep data in the Temple University Hospital data set, just because they record for such long periods of time, waiting for these rare seizure events, and so there's even though it's sometimes referred to as baseline, there's plenty of sleeping, and there's certainly other data sets. I mean, if you go to physionet.org, there are sleep data sets. Having a really large set of sleep recordings, you only really need an hour. So what I'd love to that's ideally that's what it would be in terms of like get people in during the day, get them to fall asleep in a dark room in a comfy chair, and see if you can also do this. And you go through a sleep cycle in 45 minutes. So sorry, did you find let me get that second one.
So this one has the Massachusetts General Hospital sleep lab data set.
Oh, okay.
And the sleep heart health study. Do you know if they're like open access?
It doesn't mention figure in it.
Hi, Richard. I remember what I was trying to remember about short versus long training. More is better, but I don't think there's a point where you're going to do too much because the games are so boring. But anyway, if you have, I think another thing we saw in that data was like if you're especially interested and in the brain training, you're going to do more and it's going to have more effect. But if you're just like, I don't know, I don't really care.
Since I come from special ed land, I have to ask. Most people don't even think about it. Were there any regressions? People did training and somebody went backwards.
Yeah, I know what you mean. I don't remember. There may have been like regressions in one or two tasks for some people, but overall, people stayed about the same. At worst, they stayed the same. Yeah.
That's a good sign. That's a very good sign.
Thank you.
So, sorry to be switching between two conversations, but so I posted a second. So the second one's the archive paper from the same Mass General group. What they bring up is 86 patients with multiple nights of consecutive EEG recordings were selected from epilepsy monitoring unit patients, right? And it is basically whose EEGs reported as being within normal limits, right? So like, just I'm not saying that this is the kind of data that they would throw away, but like this is the in many of these epilepsy patients, this is like not the data the neurologist is waiting for, right? But
we've been talking about doing this in Toronto as well, using the epilepsy monitoring unit data for looking at sleep stuff.
Yeah,
it's kind of obvious,
but shouldn't there be some possibly background signs of epilepsy even when they're not during an episode in a patient that's been diagnosed?
So
probably. Yeah.
I mean, like there's definitely some, there's
like if you have more than 2 in your lifetime, something has changed in your brain, and if you keep having them too, there's something causing it.
Right. So
well, I think one thing you could say is that for someone who's not having a seizure, the physiological change of sleep is going to be like, completely is going to be much larger than the kind of non-seizure epileptic abnormalities.
You mean like I think I've read about
massive
recovery.
neurophysiological event.
Is there that?
I'm just saying like
read,
sleep is such a big, brain state change that there might be kind of like residual signatures of epilepsy kind of pathology that aren't actually having seizures, but compared to the brain changes from waking to sleep, I think they would be completely drowned out. So from that point of view, there's a lot of signal and just the data quality, the amount of data in these epilepsy monitoring units, like they have people in for days with depth electrodes as well. It's like, it's a lot of good data.
I mean, just so you know, like this is a typical population that gets used a lot in a lot of neuroscience, right? And so this issue of, well, are these somehow different than if we were able to do, say, stereo EEG recordings and healthy controls is a common problem. But for a lot of the invasive recordings, like you've got to have a good reason to have your skull opened, which is always a bad sign, and it means that you've undergone that trauma, plus you're probably on a whole bunch of medications too. So that's certainly, but what they're doing is using these long-term recordings that we do have. And the fact is that hospitals are sitting on tons of this data, right? And so, props to Temple University for releasing their data. I'm still hoping more groups will do it. But I think some of them are waiting for applications like this that will give them some machine learning projects. But this is a great one. I mean, and what will you be doing with Steve Mann? Will that be with healthy controls?
Yeah, just there's kind of 2 parts to it. One is using, I'm kind of obsessed with Peter Robinson stuff. He just has so many like big contributions to different parts of neuroscience. And one of them is sleep and sleep physiology. So there's a model that, they've used the Robinson model to track sleep state changes and try and understand some of the kind of corticothalamic physiology associated with the EEG signals in different brain states. So my kind of half of this is primarily basically using this model to explore EEG data in general and just working with the model. But the specific things we're interested in is using the Muse-S for this basically, and seeing how well it kind of performs. Evaluating really like the technical kind of signal aspects of trying this type of physiological model fitting using data from that type of consumer grade EEG. And then the other part of the project is going to be doing some new sensor development, which is what Steve and co are going to be contributing more, some new hardware and some new neurotech things. But I'm thinking more like in terms of the modeling, in terms of the EEG neurophysiology and sleep neurophysiology, and that's not specific to Muse-S EEG data. It's really like half the things that I'm interested in and that are relevant to this project. They can and should be, and probably can be better assessed with high quality data sets from elsewhere. So I know about there's a big library of basically like low quality EEG data, sleep data that comes from studies of cardiovascular health. There's what is the website for this, like sleepdata.net or something.
Okay.
And they have things like 6-channel EEG, 2-channel EEG, and lots of it, like thousands of people with some blood biomarkers and stuff like that. So I was aware of that, but I'm not so. There don't seem to be like a large number of high quality open access sleep data sets that I'm aware of yet. Apart from maybe one or two on PhysioNet, there's not loads on PhysioNet.
Yeah, so I only, I know PhysioNet for sure, which is also a Boston project. So some of those data sets are drawn from the Boston area hospitals. I want to say, I know that VisBrain has some sleep EEG features, and I forget what data set they like reference or they use for that. I would have hoped with McGill's big we're releasing all our data, that one of the McGill units was collecting a lot of sleep EEG, or has their epilepsy unit released all their EEG data?
Yeah, good question. Not sure.
Okay.
Yeah.
Not yeah. You don't answer for them.
No, it's hard to keep track though, isn't it? Like there's this, we're going through this change, this curious transition, right? Where the last 5 to 10 years, you could like enumerate the main big open source data sets, right? And you kind of know them. There's 5.
Yeah.
You can list them. But then every year it's like an exponential. So it's really just getting to the point where like you can't keep on top of everything. And there's new stuff all the time.
Yeah.
I mean, this is that's great, right? It's amazing, but it's also just a head fuck.
Yeah.
Oh, there's now this. Oh, should I be using this instead of the other thing I was doing?
Well, just the fact that NeuroScout can be a tool that's just used for processing naturalistic fMRI, like that there's so many data sets of just people watching movies, and where it's like, yeah, I could remember Study Forest, and that was it.
Yeah.
Like that was it, right? That was the one open source, naturalistic viewing. But
I don't think there's that much sleep, at least. Like I was looking for high-end sleep studies, and also we wanted ones that had potentially genetics and blood biomarkers.
Yeah.
But I did a kind of search for this about half a year ago, and nothing kind of jumped out at me. So I don't think that space on that has been moving as quickly as it has been for naturalistic fMRI.
Yeah. But it's really kind of crazy, right? In the sense that like, especially people who care about modeling, right? You want to have a real model of the electrical activity. Like your models should be able to handle the really evident state changes that we all go through every single day for multiple hours, right? And so we know that it's involved in memory consolidation and all these other things, but there are very few models that that can incorporate sleep and or anesthetics, right? Being has Peter done anesthetics models too?
I don't think so. No, I think that's a gap in the portfolio. But David Lively's really the main guy for those type of David Lively and Axel Hoot.
Yeah,
probably the main people who've done the neural mass models for anesthesia.
Yeah.
Whenever I did y'all just mentioned anesthesia, I had found a video for junior high and high school kids to introduce them, and the kids actually went into an anesthesia lab, and what he showed them wasn't wake or sleep. It was the states that the brain goes through as it goes to sleep, and he said, "Here, look at it on the monitor." It's really cool stuff. Just where I'm at with learning, I actually stopped in my EEG textbook at sleep because I was like, "Whoo, it's a lot more than being awake." And so much of the motor imagery stuff, and we talk about like at the BCI conference this week, but I think 2/3 of this book is actually sleep.
Yeah.
Is it clinical?
Is that the impression you get from being more deep in it than me? Sleep is that much more complicated.
Well, so can you show us the textbook?
Yeah, here, this one.
Yeah.
Right,
So
right. It's just a clinical electrophysiology. Yeah, so that's why.
I mean, EEG has kind of been used in these two subdisciplines, right? So epilepsy and sleep, and it has super long history, and as well as the fact that sleep is well characterized by these frequency domain changes that are quite evident in the recordings. So yeah, it gets but it's fascinating, and that's awesome. That's awesome that using a Robinson sleep model is a part of the modeling work that you're going to be doing there, John. In many ways, that is again, like, it is kind of the beauty of those models. They don't really need high density, as long as you're not really missing anything.
Yeah. Pretty gross changes.
Yeah, I mean, it's as I assume the Muse S is still just 4-channel system.
Yeah. Yes.
I mean, is it still like?
I think they shifted them around a little bit.
Yeah.
Okay.
Still.
Has it not got the temporal ones?
Okay.
I'm not sure.
Yeah.
It's just a soft version rather than hard plastic. It's now fabric. That's the headline.
Yeah, that's the headline. Yeah.
So I'm still a little confused as to why getting brain age from sleep is so. Why you guys are talking about this? Because I for example looked at EEG in our subjects in awake or default mode network, and it was like, yeah, it's right there. You don't have to do 45 minutes of sleep. You can do it with 5 minutes to 15 minutes of doing some other task. Alpha powers, especially in the default mode network, is one good quick way of getting it at brain age. Is it the case that you have a lot of data and now you're like excited to like, oh my gosh, we found brain age in this chunk of data? Or
no, I mean, so the idea being that because of the particular the changes in the system dynamics with sleep stages, that you get these various kind of reduced. I mean, as you go through these stages, you're seeing these different systems that are active with different neurotransmitter configurations, and that the differences that you see are more physiology than cognition. And
I see. I see what you're getting at, but you can really just do this with eyes open, eyes closed. close your eyes, record, open your eyes, record. There's a
Yeah. So so I would want to say you actually want all of this. That those sleep snapshots of are really different facets of the same system, right? And that's not to downplay resting awake and eyes closed, eyes open, but that's just one snapshot. I would want to also include various drugs and pharmacological challenges too. I mean, in terms of, again, what we're trying to get at is a measure of or measures of very complex organs, physiology and health, right? And so I mean, and certainly one of the things that they emphasize is like your brain age calculation. I mean, and the MRI people have been doing this for a while too, right? It's just a risk factor. It's just it's like if your estimated brain age doesn't match your biological age, then there should be follow-up, right? And what they're trying to do with this is also get at and just a cheaper version from the MRI. But I would hope, and I think it's probably somewhat maybe because of the data sets. I assume they're just riding on clinical data sets, and this isn't like a study. But
I have a kind of related question. You guys have probably seen the recent finding where they found CSF, cerebrospinal fluid, is like circulating in and out of the brain, especially during sleep. So I was happened to be looking at a world map of ocean currents, and there's like, warm currents and cool currents, and it affects weather, this and that. So, have people looked at the currents of CSF and blood throughout the day? Yeah, what's going on there? Are there warm currents and cold currents? These currents are oscillating on the order of seconds, minutes, days, weeks, hours, all of the above. It's got to mean something. I'm sure would.
Well, so you're limited by the measurements you can take, right? But what I can say, what I'm familiar with is what Anders Dale has published with people at Simula, and so they've been looking at trying to model the lymphatic system and also some CSF. Very, very interesting features that have a lot of health implications.
Okay.
And they started with the finding that there's a particular dementia that is caused by excessive CSF pressure, and that it is curable. So it's like the one dementia that's curable by releasing this brain pressure. But it got them started working on the computational fluid dynamics of the other fluids. So as far as I know, they're not like ignoring the blood, but they're kind of focused on everything else that is modelable, and in particular the lymphatic system, because of obviously like how important that is for overall health, right? And they were very proud of that at the time in terms of
maybe Oh
So-
yeah, we figured out that the brain was an electrical organ, and now we're like, oh, but it's also a fluid organ. So-
Yeah, I mean, but yeah, and the and obviously there's some interesting molecules in that fluid that are.
I was going to say it's a vat of chemicals as well. If psychiatrists think
It's
of.
what's scary. Oh, you just hit the same chord I was thinking. Is that it just scares me when me and Morgan have talked about this last week in the neuro bar. They're hit and miss with psychiatric drugs, and you're putting serious stuff into your brain.
So
I want some.
On that point, I mean, Ed Bullmore, who's the book I mentioned, The Inflamed Mind. Ed Bullmore had some references that he shared this week, and I'll try and find it. But
is he in the thing this week?
Which one?
Ed Bullmore, was he?
Oh no! I mentioned him in the Neurobar in terms of his book, The Inflamed Mind.
Yeah, I did a trial of Blinkist, and I listened to the Blinkist blinks for Inflamed Mind. I can't remember. I loosely remember some of them.
Oh yeah.
But yeah, that's a book I need to actually read, I think.
What is the Neurobar?
So that was a social that was being held after the BCI 101 webinars, and yeah. So unfortunately, the third and final Neurobar was today, which is why Richard and I have been on Zoom now for 6 hours.
Heroes.
One of the things I learned about learning is that immersion is good. So I'm immersing myself in the neurotech community more than ever before, and just felt appropriate. So,
but
more of a lay person.
I do want to point out Anders' work on this, because I never really hear much about it, but he's super proud of this lymphatic modeling, and and he's doing that together with Simula in Norway, which is a group that I mean that particular research institute was founded to study turbulence and computational fluid dynamics.
Okay.
They develop are very very involved in the Python package for finite element modeling called I'm blanking, not Fiji.
Yeah. It's okay. It's in my mind, it's probably a little too early to be modeling things at such a low granularity and shear and flux and all this. I mean,
they've
still need to measure. No, I mean, sure, you could model, but what is going on at a gross level? I mean, where are the hot and cold currents? And at least I'm not familiar with any of this.
So I'm not sure what you mean by hot and cold currents.
Just by analogy to ocean currents, what currents are important, and what so are there individual differences, age differences? I'm sure there are. Differences as an effect of training, sleep deprivation, caffeine. Sure, you can model it down from at the capillary level and all this, but well, what do we understand it at the gross level? At least I am not familiar with that literature. Mhm. Mhm.
Yeah, yeah. It is. I mean, I think what you're seeing with Muse S and with I think Philips has got a similar product. Is that, yeah, this is one of those areas that not only has the history, but it really could have, like the killer application to be able to monitor and get some meaningful, these are clinical signals. So I want to be especially cognizant of time, as it's 9 o'clock here and it's midnight for those joining us on the East Coast. I hopefully we can come back to Kyle's. I don't know if everybody saw the reference Kyle dropped in the chat, but I'm interested, and I like the idea of not necessarily super accurate devices, but certainly ones that that could be a part of your house system for monitoring, especially if we're also home all the time.
I've seen something. It's a Python script that was published by somebody working with NASA. They made it so that they could just use a camera and looks at the your forehead, and it can do your beats per minute like that.
Sure, sure. Um, yeah, yeah. Yep. COVID.
I've been thinking the same thing. It's on my to-do list to get an Aura ring. The single reason why I haven't got one yet is because I don't know my ring size, and I don't know. It's just kind of a bit of an investment when you. And I'm not. And I'm kind of slow in, going to jewelry shops. I know my ring size. Oh. Right. Well, we'll wait.
What's the difference between my Apple Watch and the Aura Ring?
The Aura Ring looks cooler.
It's smaller. Yeah. Oh. Skin temperature. Come on. Can they do blood oxygen? I guess that's PG, not PSG. Oh yeah, there they are. Yeah, they're doing more than the Apple Watch, because the Apple Watch study, I wish I could had a quick link to it, but it really just looked at HRV and I think risk of heart disease or something like that.
Yeah.
They get your pulse all day, every day, and they, if your heart rate variance is through the roof, then they send you an alert to say go see your doctor, I think.
Well, if you don't mind, I'm gonna sign off. I'm gonna wrap up the recording. That does not mean that you need to leave the room, but just want to say thank you to Alex for being our recording engineer and post-production specialist. And yeah, so we've got don't have anything lined up for next week yet. Not this Monday, but next Monday is going to be the 150th NeurotechX Paris Hack Night. So we're trying to schedule a couple of people for that. One being Gene Rintel, and talking about Spectra and OpenEIT, and also the I'm going to ask the Neurolib developer if he could join us and talk about his project. But I'm always on the lookout if anybody's interested in presenting something, or if you have topics that we should put on the agenda and stake out time to discuss. Just let me know. I know Joe's sorry. Sure. Yeah, well, it's Paris time, so but yeah, so CET is exactly the same as this in terms of 6 p.m. to 9 p.m. What that means in Pacific Daylight Time is 9 a.m. So 9 a.m. to 12, and and noon to 3 for those on the East Coast. And we'll get the YouTube up of the open source ultrasound project, and Luc Janvieux, which is great. It was great to hear from him, talking not only about what he's doing with an open source imaging system, but also about because he's got an FPGA on that board, and because there's a number of other kind of specialized parts, in particular the transducer. He's got some. I mean, one, they basically wrote on top of a particular another project that gave them the open source implementation of the FPGA and what they needed for that. That was really helpful and could be probably incorporated into some other projects. And then lots of stories about sourcing things. Yeah, I mean, he's not trying to build something medical at this point, but there was a recent paper that I had to get. Anyway, GE's got a new paper. It came out yesterday, covering peripheral focused ultrasound for neuromodulation, and it's a nice overview of all the different things you can do. As well as like it just shows you that like GE and Glaxo and Verily are all trying to be in this bioelectronic medicine space, so that's the easy thing that is something that Luke was able to talk about. He was able to talk about FUS. As well as, the kind of ultrasound imaging, and in particular, the full waveform inversion stuff from Imperial from a couple months ago that is super exciting for brain mapping. Yeah, so hope you can join us on Mondays. If there's anything that we could talk about, I mean, I'd still love, to even send out a paper in advance and maybe talk about it. I don't know if that would work as a discussion topic. I know there's, somebody asked about 3 months ago for a discussion of, a couple of papers that relate to our subcortical structures, EEG visible. And so there's a couple of papers that I'd be certainly willing to just step us through a couple of the figures and talk about those results, because they're pretty clear. So this is some stuff from Christophe Michel where they've got deep brain recordings and then ultra dense EEG. And yeah, so I don't know if that would be of interest to others, but I'd love to hear from you for anything that we should have on the agenda and that we could talk about more. So on that note, thank you so much. And any last thoughts? No.
Just great chats, guys. Really good session.
Cool. So yeah, we'll get the YouTube up and going forward without BCI 101 and with I've seen a little bit of movement with Moab and Pyrimon. I don't know if there's so those could definitely we talked a little bit, John, about with Jaden about motor imagery as being something that we could add to the EEG notebooks. And yeah, so and I was just saying that, like, what you have from Moab that we don't use is all this existing data that's particularly relevant for motor imagery. And something that Moab hasn't been used for is basically giving you some prior knowledge or some features to look for from other data sets that you then apply to Amuse or OpenBCI.
Good idea.
Yeah. Okay. Well, take care, everyone, and have a good evening. See you next week.